Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be talking about a special topic which I decided to speak about simply because somebody is studying this material and I want that person to understand. So, just a little bit about GeoGebra. You can go to this link here and you can type in that URL and it'll bring this up, which is an online version of GeoGebra. And then, for example, if you have this applet stored on your local machine, which I do in downloads, it's this one here. Okay, so this is what I'm going to be talking about, the auxiliary equation in the new calculus. And before I start that, it's probably a wise idea to note that in my free ebook, to which I'll place a link also in the details section, I discuss all these things. I give you the full definition of the new calculus derivative, okay, which is all this information here. And I talk about it in extensive detail. I show you how to understand the terminology, how to use the different parts of the definition, and I also show you how to work with the auxiliary equation and to see how in the new calculus inflection points are handled correctly, unlike in your mainstream calculus where you sometimes have a tangent line and no derivative, and then you have a derivative and a tangent line, so there's no consistency. But in the new calculus, there's always consistency. And I show you how you can use these facts to show that there is an inflection point. In other words, if the only pair, for example, and I'll get to that in a moment, if the only MN pair that makes the auxiliary equation, this part here, null is the 0,0 pair, then you know there's an inflection point. And that's much, much easier than, for example, finding the first derivative, the second derivative, and then testing to see if the sign is different or the same on either side. Okay. Now, I also want to open another particular applet here so I can show you something else. So this is going to be a little bit of a long session, but just bear with me. You'll learn a lot. Okay. So let's go here. And right, we're over there. That's good. I'm not going to deal with that right now. Don't worry about it. So what I want to show you now about this is I'm dealing with the cubic here. So this person has asked, how does this all work with a cubic? Well, first of all, you can use GeoGebra to simplify your study a lot. You don't have to do a lot of calculations. So you could, for example, type in this auxiliary equation that you find from your introduction, which is this here. You could just type that into your first input bar. And the way you type this in is simple. You just say 3x times that plus, and to get the m squared, you say m, and I'll show you how to do that again. You say m caret squared, okay? And it does that for you. So that's how you get the squares. To get the times, you say star like that, okay? And then, of course, it understands. So if you want to say x, that's fine too, because x is the parameter, okay? So x, m, and n are passed to the auxiliary equation. And I'll show you here where I'm passing x is 1, m is 1, and n is square root 3 minus 1. Now, one very important thing that a lot of mainstream academics like Professor Jack Hazinger, Marcus Cliver from Sweden, Hazinger is an ex-Harvard alumnus, and a lot of people miss is that you can't just choose these values. You always have x, which is the first one, but then you have to pick one of m and n, and then you find the other using the auxiliary equation, okay? Because you can't just choose them. They're specific to the particular function you're working with, okay? And there are many of them, by the way. It could be, there are always innumerably many of them, unless there's an inflection point, which I'll demonstrate in a moment. So what you have here right now is the cubic, as I've shown in the blue curve here, which is y f of x is equal to x cubed. And I placed the x value here at 1, okay? I can place it anywhere else I like, but it doesn't matter. I placed it at 1. And I want to show you that if you choose a particular m, so let's say we choose, m is the distance from 1. So it's the horizontal distance from the point of tangency. So if we want m to be 1, we place it there, right? And then we'd find n. And n turns out to be this value here, which is equal to square root 3 minus 1, okay? And the way you can get that is you can have these helping functions here, which are basically just a quadratic formula. Turns out that the one you need to use is the plus one, because this one here will give you a negative distance, and you can't have a negative distance for n. So turns out that if you put 1, 1, 2 minus 2, you'll get square root 3 minus 1 here. This is square root 3 minus 1. Don't believe me? Let me show you. Root 3 minus 1. Okay, as you can see, it's exactly the same value, right? Okay, so that's how you put these things into GeoGebra and you make your life simple, right? Very simple. So now, is m equals 1 and n equals to square root 3 minus 1 the only pair? No, 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 it's not. Let's say we took m is equal to a half, somewhere over there, right? Let's try and get it to a half, approximate. Or it doesn't really matter. We can say 51016. So we can come here and we can type in 0.51076. And you know what I did there? I need to just put a 1 there. 1 like that, and take this one out. Okay. And over here we'll say, instead of this, we'll just say 0.043481, like that. And if I press enter, it's still going to be 0, okay, because it's just another pair. Right, let's see. There it is. This is the one I typed in just now, okay? So there are many pairs here that will give you the same slope of the parallel secant line to the tangent line. And by the way, many foolish academics will ask, how do we know that there are parallel secant lines? Well, you know, we knew this over 2,400 years ago. The Greeks knew this. That is, that you could place a point like that, and through this point, draw a line parallel to any other line. In other words, through a point not on any of these lines, either of these lines, and then draw a parallel line through it, right? So you select any of them, this one, click there, and you got your parallel line, okay? So that's how we know, and it's been proved in the elements, but of course, a lot of stupid people have never studied the elements, especially mainstream academics, but I'm not going to harp on that. Now, so as you can see, there are many, 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 many pairs. And if we get there, we still have, the auxiliary equation, which, by the way, works for any of the mm pairs, including the 0, 0 pair. And you might say, well, do you actually divide by 0 in this equation here? So let's just go back here. If you set, in this section here, if you set m and n equal to 0, is it the same as having divided by 0 in this particular section here, in this step? No, it's not the same. Why? Because by the time you reach here, you've canceled out these factors. And by the way, they always cancel out, no matter what kind of function you have, whether it's polynomial, whether it's transcendental, trigonometric, exponential, logarithmic, whatever it is, they always cancel out. I have a proof of that. And it's also true in your garbage mainstream calculus. So for example, Newton's and Leibniz's formulation was rigorous, even though people didn't know it. So if you say f of x plus h minus f of x, like that, all over h, you'll get the derivative, which is the slope of the tangent line, plus the difference. In this case, q of xh. Now, this is a parody on my new calculus. I tried to see if I could do the brilliant things in mainstream calculus with the new that you can do in the new calculus. Turns out you can't, right? So you can say, well, is it okay just to set h0 here? Yes, it's perfectly okay. Uh, because I say so? No, because this here is a slope difference and you're discarding it anyway. So setting h is equal to 0 here is perfect in that respect. And it's also perfect from the point of view that you're not dividing by 0 because h has cancelled out. And if you don't believe me, I have a video on that where I show you these things. Very nice little video. It's, let's see, where is it? But this one here, okay? When one treats expressions as numbers and not indeterminate forms, algebra actually works just fine. So I'll put a link to this and you can watch it, okay? So what I'm telling you is that you don't have to worry about setting h equal to 0. It's 100% rigorous. You don't need limits. Limits is just basically obfuscation, proving that the academics, the mainstream academics of the last 200 years didn't know why calculus works, still don't know why calculus works. That's why they use limits, because calculus doesn't need limits. Okay, so now that I've shown you that, let's see what happens if you have a point of inflection. So I'm going to move this along here, move this guy over here, and see, it's not possible to draw a parallel secant line here. It doesn't matter how you choose m and n. Is that a problem? No, because it tells you that there's an inflection point at x is equal to 0. Okay, this is x is equal to 0. There's an inflection point. Right. So if we move it away to somewhere else, we can have a secant line. So the beauty here is that if you have an inflection point, the only pair that will work in your auxiliary equation is 0, 0. But by the way, you say, well, don't we have to worry about this being 0? It's always 0. You don't have to worry about it. This slope difference is always 0. Why is it always 0? Well, look at your graphs. These are parallel secant lines. I mean parallel lines, which means that they have the same slope. The slope difference must be 0. And that's what this expression here is. It's the slope difference. Okay, it's the same thing that you do in your bogus calculus. This is the slope difference. It is. If you don't believe me, try it. And by the way, also here, as with my new calculus, h divides this finite difference. When I say divides, it means it goes into it without a remainder. In other words, it means it measures this difference as a whole and not parts of h. In other words, you can take it's not if you say 9 divided by 4, right? 4 measures 9 twice and a quarter, right? Twice and a quarter. But if this were this finite difference here, okay, and h were some value down here, obviously it's not going to be 4 in this case, it would divide 9 without equal parts of itself, okay? That's what it means when I say h is a factor of this top part. And there are many brilliant articles I've written on that on academia. I'll also place a link to those as long as I remember. Now, so what you've got there then is the auxiliary equation explained, and you can have it for any other function. It's obviously not going to be the same. You'll notice that with a very simple function, such as y is equal to x squared. Okay, so let's go to y is equal to x squared. F of x is equal to x squared. It's usually a parabola like that. If you have any tangent line like this, and you have a parallel secant line, okay, parallel secant line, you'll notice that at the point of tangency, this part here is always equal to this part here. Archimedes knew that, by the way, and it's in one of the propositions on quadrature of the parabola. What this means is that if you find m and n in the case of a parabola, and this is the point of tangency, okay, x, and this is m and n, these are always equal because of this special function, okay? It's a parabola, and it's the same for all parabolas. Some other functions also have that property. I'm not going to go into them now because that's not the purpose of my video. So let's see, have I dealt with everything? Yes, and let's answer some questions here. So the auxiliary equation is a feature of the new calculus, okay? You don't actually need to know it. You can just discard it like you do with your terms in H in your bogus calculus, and that's perfectly valid. Or you don't need to know it to find the derivative because all the terms containing m and n or h in your bogus calculus um, can be discarded. And that's simply why it's perfectly valid just to toss them away or set them equal to zero. It has the same effect. Now, in the new calculus, the difference is that in the new calculus, it's rigorous. M and m, all the terms in m plus n, no matter which mn pair you use, it's always going to be zero. Okay, so if we put this back on one here, and we look at this value down here, this q here, it doesn't matter how we move this value here. And incidentally, here I could change this by saying this is, let's see, this is, I think m and n. Okay, m and n, like that. Okay, so as you see, it doesn't matter. Different m and n's, and it's always zero. Okay, always zero. All right, m and n are the distances. This is m, and that is n. Okay, just the absolute value between this point and the green point. So the new calculus is 100% rigorous. It's beautiful. It's amazing. You can do a lot of things with this auxiliary equation. Again, that's not the point of my video, so I'm not going to discuss it. So now, what I've just done in this little explanation here is explain what I've been telling you. So I'll paste this text as well in the detail section, so you'll have all the information you need to understand these things. It's a lot of work, but it pays off because in the long run, the thing about the new calculus is that in the beginning, it seems like a lot of work. It's not the case of you just saying, taking your garbage limit, for example. You don't just go, you don't just do something like this. Let's just reset the count for this. You don't say because f of x is equal to x squared, you don't, and you take a limit as h equals to 0, and you say of 2x plus h is equal to 2x. You don't do any of this bullshit. It truly is bullshit, by the way. And you don't need to use limit at all in calculus, not in the derivative and not in the integral. And if you go to my main free publication, which has been published a long time ago. By the way, I also have special functions of sine x and cos x, but that's very advanced feature right now. Don't worry about it. You will see that I deal with the integral as well, and the new calculus integral is amazing. It also is based on this same definition. Okay, it's like the historic geometric identity, and I explain that to you here, why it works, and you don't need the limit of infinitely many sums because that's also a bullshit concept. And this, by the way, is a new calculus, part of the new calculus integral. So if you multiply both sides by k, you have the integral, okay? And it's given to you down here, okay? So this is the new calculus integral, all right? This is the average value, but if you multiply by m plus n, then you'll have the new calculus integral. So you need to study this. It takes time in the beginning, but it pays off because in the long run, you'll be able to do derivatives. You'll be able to find derivatives and definite integrals using the new calculus and understand what you're doing. Whereas if you take a course in mainstream calculus, you never understand these things, and you only master them after you spend years using them. Well, you master them in the sense that you know how to use them, but you still don't understand why they work. Okay. So fools in mainstream academia never realized that the new calculus derivative is actually based on the mean value theorem. Okay, so this beautiful equation here, this ingenious equation, where are we? Let me just get there again. I think I went down too far. Let's see here. Okay, this here is based on the mean value theorem. In other words, rather than trying to find the derivative at a point x here, we just used x, which is between x minus m and x plus n. And if you look at this in the mainstream calculus, they normally say f prime of c is equal to f of b, where this part here is b, and this is a, where f of b minus f of a over b minus a is the average value. It's not an average value; it's actually an arithmetic mean. It's the mean value of all the y ordinates of that function. Now, I almost forgot, but we could using angle derivatives, which is a concept also that I discovered. I haven't told you everything about it in my videos, but I have discussed it before. You can plot a function in terms of its angle derivatives. Okay, so for example, if you say, let's say you wanted to plot, let's say t cubed, right? Then basically you would say t to the 4, like that, t cubed, right? You're doing t cubed now. So if you do that, then you've actually plotted here the slopes of, you're not plotting t4, you plot the slopes of the cubic. This is for the cubic, okay? So if you put the trace on and you move that along, so this here is the plot for the cubic, and you can do it for any function. Like if you said t to the 3 like that, okay, and you move this away, again, this is for the, not the cubic. This green curve here is not the cubic, but the quadratic. Okay, this stuff is very advanced. I mean, most math professors won't understand it, so I'm not going to spend time on it. But I'm just showing you that you can take any function and squash its range into this particular section here. So what angle derivatives allow you to do is to take the range of any function. Here's, for example, you could have something like this. Let's give you another demonstration here. So if we have 5t to the 5, like that, minus 3t to the 3, plus t squared minus 6, like that. Then we've got a function here which is really going all over the place and has lots of inflection points and stuff, but we can actually see what it's going to look like just by doing this. Can you see that? You can tell everything about the function by looking at the angle derivative plot. Okay, you can tell where there are inflection points, and if you do this, that's the entire function, the blue function here that you're looking at. So let's just replot it again. Okay, so that's what you have there. Okay. It basically gives you all the information you need to know about the function without first derivative tests, second derivative tests, checking for signs, and all that bullshit that you have in your mainstream calculus, which is tedious, long, and your teachers enjoy torturing you with special questions which take 3 hours to compile, and they expect you to solve in 5 minutes in a test. It's totally ridiculous. And of course, the only way you can master those sort of things is by studying past papers and becoming an expert. Yes, I got very good marks because I knew how to take tests. And of course, if you don't know how to take a test, it doesn't mean you don't know how to do these things. It means that basically you haven't learned the tricks. Okay. So let's just close that. We're not interested in that. Coming back to this here, and that is all about the auxiliary equation. So if you have any questions, post them in the comment section and I'll answer. And please don't ask too many questions because I do have eye issues and can't spend too much time on a computer. So my dear friend, my dear friend John, I'm not going to mention his last name. This is a video produced especially for you. I hope you will find it useful. And if you have any questions, you can always reach me at any time, ask me, and I'll help you. To all others, if you're not already a subscriber, become one, click like, follow me on academia, tell your friends about this. And I'm out of breath now, and I think I'm wheezing. We'll talk again soon on this channel. Till next time, I'm John Gabriel. This is New Calculus Channel. Goodbye.